4. That's not about your coefficient. It's not whether your coefficient is divisible by 3. Okay? That you just cube root. But the variables, we're basically breaking this into, what is 12 divided by 3?
4.
Right. So this is, I'll do it one time as the product rule, but then I'm going to stick with the power rule. This is the same thing as x to the 4th times x to the 4th times x to the 4th. Okay? Triplet factors. Okay? 4 plus 4 plus 4 is 12. We divide it into 3 groups of 4. If this is divisible by 3, you can divide it into 3 groups of 4. By the power rule, the index is 3. I write x, and I want that 3 to match. So I write, this is one or the other. You don't have to do both of these. In fact, I prefer this if you're doing it all. If you recognize it's a perfect cube, you'll get to the point where you can skip this step. But 3 and 3. I put a 3 here because I want to match my index, because then they'll cancel out. And what number do I put here to make this still equal to x to the 12th? Okay. See, if it's divisible by 3, then I can reverse my power rule. Okay. Either way, it equals x to the 4th. Okay. So here, we've got a cube root. I'm just going to do a power rule. It's a cube root. So I want to write my number as something cubed, and then I've got an x, which I'll leave some space, write it as something cubed. Careful. What is the cube root of negative 216?
7.
Negative 216. Negative 6, yeah. Negative 6 times negative 6 times negative 6 is negative 216. And how would I keep this equal to x cubed? What do I put here? 1. Okay. So for our final answer, we've got negative 6x. Cube root. So I want to rewrite my number as a cube, my x as a cube, and my y as a cube. From the cube, once you have everything written as a cube, that will cancel out. And so what is 512 written as a cube? X to the 6th written as a cube. Well, we've already got a cube on the outside, so yeah, so we were dividing 6 divided by 3, and y to the 7th. And then you can always check as you go along. Yes, you're not changing the value. 8 cubed is 512. X squared cubed, 2 times 3 is x to the 6th. Y 7th cubed is y to the 7 times 3, y to the 21st. Make sure that is true, and then you've got your answer. Then you root and release. Your answer is 8x squared y to the 7th. With no leftover bits. Now 21 is not a perfect cube, so of course we have to approximate. What is, if you think of your list of cubes, what is the biggest cube less than 21?
2.
2 is the answer, but that 2 is the answer to what? What cubed? What cubed equals 2? 8. What cube rooted equals 2? 8, right. So cube root of 8 is the biggest one less than 21. And what is the biggest one, what is the one after 21?
3.
Which is cube root of
27.
27, right. Okay. So cube root of 8, cube root of 27. Okay. So this equals 2, right? And this equals 3. So cube root of 21 is going to be something between that. Okay. So math, choose number 4 of 21. Close the parenthesis. And 21 is actually closer to 27 than 8, so you expect it to be a little bit more than 2.5. So yes, 2.7. I'll write 2.76 just to round to the hundredths, which is between 2 and 3. So there's your approximation. It has to be rounded, not an exact answer. Can't do the math with it unless you're told, give me an approximation. You can visualize the approximation because it's in between 2 actual cubes, and then confirm it on the calculator. All right. So real quick, here's some nth root examples. I want to make sure we get to the product rule. Real important to leave you with that. But nth root is just dealing with bigger roots than 3. Okay, so 4, 5, 6, 7, anything bigger. So fourth root of 256. If you recognize your perfect fourth roots, you can go right to the answer on this one. It is fourth root of 256. If you're not sure, remember, at higher root, you have to put in the index first. And then go to math, number 5. 56, no parentheses, and you get 4. Because there's 4 times 4 times 4 times 4, quadruplet factors, is equal to 4. Okay. And this is 4 to the 4th power, so then it would leave a 4. Now, could I do the fourth root of negative 256?
Yes.
Is there a fourth root of negative 256?
Oh, no.
Even index requires a non-negative radicand, whether it's a square root or any other even index, because you can't have pairs that will make a negative number.
I thought you were on the second one.
Oh, okay. This one, fifth root, is this okay?
Yeah.
Yes. So its fifth root is
3.
Yeah, but specifically, negative 3. Negative 3 is the quintuplet. Okay. Now, this negative is on the outside. Is that okay with an even root, an index of 6? Yeah. And now this can break down to negative 1 times 2 to the 6th, x to the 1 to the 6th. See, that's a perfect 6th root, and that's a perfect 6th root. You can verify that in the calculator. There's no leftover bits. So your answer is negative 2x. Seventh root of 87, you can see it's an approximate one, so you have to do it in the calculator. Seventh root, math, number 5 of 87, approximately 1.89. I'm not going to bother trying to approximate with actual seventh roots because, I mean, that's just out there. 1.89 if I round. Fourth root of negative 625. Nope.
Oh, it's not because it's
Yeah.
an even number.
Right. Even index.
Yeah.
It is an even index, so you cannot have a negative radicand. It is non-real.
So whenever, like, on the test we have that, what do you want us to write on?
Just write non-real.
Non-real?
Yeah. On the next unit, the next test, you'll tell me that this is 5i. Okay. But not on this one. This one right now, you just say it's non-real. Okay. It's imaginary answer. Okay. So fifth root, again, these are perfect fifths. 32nd's a perfect fifth. The fifth root of 32 is 2. The fifth root of x to the 5th is
It's just 2x.
right, x, and then this is 3. Okay. So it's 2x y cubed. And a quick check-in here as we move to 11.3 and the radical. We're going to come back to 11.2 at the end of the unit. So, which of these is not real?
The second one.
Right. Negative, different variations of negatives, all of them are legal except for the one that's under the radicand with an even index. That's the one that's a problem. Okay. So, product rule. Now we're going to get into things where we don't have perfect roots, perfect squares, perfect cubes. And we're going to have leftover bits. And we use our product rule for radicals to help us deal with that. Okay? So the product rule goes in 2 directions. Note here that you are multiplying 2 different radicals. Now it doesn't matter the radicands are different, but what does matter is they have the same index. Okay? So remember, I'm pointing out this is like the opposite of the exponent rule, product rule of exponents. We have to have like bases but different exponents. Here you have to have this like indices, but of course the radicands can be different. Okay? So in this case, you are doing this to multiply radicals, but you must have the same index. Now the reverse of this is true also. If you have a single radical with whatever index, And you can break that radical down into a factor pair, and everything can be turned into a factor pair. Okay? Now, it doesn't mean it's twins. Doesn't mean, or, it's that it's a perfect root. But you can turn it into any factor pair. For example, 15. If this were 15, we could turn it into 3 and 5. Okay? So you can break one radical into two radicals with the same index. And instead of multiplying them under one radical, we're multiplying them under two different radical houses. Okay? So it's going in both directions. And we use this technique to help us simplify radicals, specifically radicals that are not perfect roots of whatever their index is. Okay, so first to multiply, 3, square root of 3 times square root of 11, we have the same index, right? So we can combine this under one radical sign, which equals square root of 33. Now at that point we see, hey, we may be able to, at this point once we put it together, this is a good technique to see if we can simplify it further. Square root of 33 is as simple as it gets, so you'd walk away. Now it may involve variables as well. This just means 13 times x under one radical, because they have the same index, both square roots, giving us 13x. Can't be, nothing there can be simplified. Now if we do the fourth root of 27 times 3, then that gives us the fourth root of 81. Now this is really useful because using that product rule for multiplication, because 27 is not a perfect fourth root, nothing else we can do with that, and 3 is not a perfect fourth root, nothing we can do with that. But when we multiply them together under one radical sign, we have the fourth root of 81. And is that a perfect fourth root? Yeah, if you can simplify it further, then you do so. Now this is a very useful one. This is definitely going to come back as we start doing more multiplication techniques. We're going to be using distribution and foiling with things, with binomials, with terms of binomials that have radicals in them now. And so understand that when you multiply a radical times itself, this is what happens. By the product rule, this becomes 7 times 7 under one radical. Hey, you've already got twins, right? One of those twins is the root. By the product rule, this means square root of 49, which is, look, it's the same. It's the radicand. Basically, when you're multiplying a radical times itself, your answer is the radicand. Right? It explodes the radical sign. Another way to write it, which will help clarify this, is that this is the same thing as square root of 7 squared. Right? So square root of 7 times 7. So if I put in the index of 2, whether that outside exponent is on the very outside or if it's underneath with the 7, whether it's 7 squared underneath or square root of 7 squared, either way, that index and that exponent cancel out, which kills the radical. Then that gets rooted and released. Same answer either way. Okay. So we're going to come back to that principle. That's going to be important next week. Okay. Here, cube root, and I just multiply everything under one radical. 5 times 3. Squared y. Okay. Just put it in order. If your exponents are less than your index, here's an exponent of 2, an exponent of 1, then you can't pull anything out. Okay? You can't root it. 15 is not a perfect cube, so you're done there. But you guys definitely cleaned it up. Here, this is just fraction rule. Whatever rules you have for multiplying anything, fractions or exponent rules of adding exponents, anything, 5m times n over 2. Okay. So this is just fractions, multiply straight across. If any of these had exponents, you'd add the exponents. Whatever rules you already know apply, you're just doing it under one radical now. Instead of being separate things, you can put them together and now you simplify them as much as you can. So this would be 5n over, and we brought it as 2m, to be but it's still under the radical. Nothing could be simplified. It couldn't be rooted and released. Okay. What about this one? 8xy?
2x.
2x?
What? The 8, you can cube root the 8.
Right, because you're cube rooting, but.
Oh, you're right. Yeah.
Yeah.
It's not the same.
Yeah. Now this, don't write non-real. This is perfectly real. There's no negative radicands. This is perfectly real. But can we combine it? No. Different indices. What would the new indice of our new combination be? Yeah. So just like having unlike bases for exponent rules, unlike indices mean you just have to walk away. Okay? So this just means unlike. You got unlike indices. It's not non-real. There's no problem with it. It just means, and here's the plural of index. I do not vouch for the spelling, I'm pretty sure. But yeah, you can't do anything with it. It's just walk away. It's as simple as it gets. Okay. Okay. Now where this becomes very useful is when we're dealing with things that are not perfect squares, but that we do want to simplify. We don't want to approximate because we can't do the math with an approximation. Okay? This would be in between the square root of 49 and the square root of 64, which means it would be 7 point something. But that doesn't help us. Okay? So we're going to use this product rule to simplify. This first group of examples, we were using it to multiply. Okay? Now we're going to reverse it, take a single radical, break it up into two radicals, so we can simplify. The whole thing isn't a perfect square, but maybe part of it is. Maybe we can simplify part of it. Okay? So the idea here is that 50 is not a perfect square. Okay. But maybe it has a perfect square factor. It doesn't have twin factors, but it has other factor pairs. Maybe it has perfect square factor. Okay? And so let's find out. Now, you can make a list in your head, you can make a list on paper, and you can make a list in your calculator. If you make a list on paper, try and be very organized about it, because it's very important when you do this that if it has a perfect square factor, you pick the biggest one. Sometimes they have more than one perfect square factor. And if you don't pick the biggest one, you're going to make a lot more work for yourself. It's going to be messy. Okay? So if you're making a list, make sure you go in order. Always start with 1 times itself. As soon as, now, if you go in order, then your biggest as soon as you see 1 on the left, you know you're done. If you don't see 1 on the left, then you're coming back around to this side. You're looking for the biggest one. So if I list the factor pairs of 50, next time we do 2. And yeah, it's an even number, so 2 is a factor. And then I check. 3 is not a factor. 4 is not a factor. 5, yeah, 5. And if I keep going, 6, 7, 8, 9, 10. Oh, 10 is, but I've already got it. Then you know you're done. And when you do an organized list, you know this is the biggest one, and it goes from biggest down and then up. Okay? And if you do it on the calculator, this is just like when we factor. You go to y equals, but you don't need a B column. You don't need the x plus y1. You're not adding anything. You just want to see factors of 50. Okay? So you're going to do 50 divided by x, and then go to your table. You don't care about a third column. You're not adding this up. You're not factoring a polynomial. You're just look for the error, because you don't care about negatives either. You're looking for positives. So start with 0, and anything that's not a decimal is going to be a factor pair of 50. Now, because this is automatically in the same order you would write it in pencil, then you know that as soon you look on the left-hand column, and as soon as you go down under error, as soon as you hit a perfect square, you know you've got the biggest one. Okay? And if you keep going and you don't see 1 on the right, and 25 works, but if you don't see 1 on the right, okay, there's 5 to, oh, now it's reversed itself. Now it's bigger over here, and you start going up. Okay, so you look from down on the right, then go up on the left until you find the biggest one. And if you don't find one, then you can't simplify. Okay? But 50 had 25, and 25 is the biggest one. It's the only one, but others have more than one. This is the biggest one that 50 has. So it doesn't have twin factors, but we can instead write a different factor, an AB. Instead of twins, A times A, it's AB. Now, always write the biggest one first. Okay? So 25 times 2. Okay? So what we're using is the product rule. Okay? And always put the perfect square, not the bigger one, because it's not always the biggest number. So put the perfect square, I'm abbreviating there, put the perfect square factor first. Okay? So 25 times 2. 25 comes first. Now by our product rule, we can break this up into 2 houses. 25 gets its own radical and 2 gets its own radical. 25 is a perfect square, therefore it can be rooted and released. No more radical. 2 is not a perfect square, and it can't be broken down any further. If you didn't choose the biggest perfect square factor, then you have to still keep breaking down. That's what gets messy. Make sure you choose the first one. You can fix it, but it's messy. And so square root of 2, it does not get released. It stays under the radical. Leftover bits stay under the radical, and your answer is 5 square root of 2. Now, 5, so this is a simplified answer. This is an exact answer. Square root of 50 with an equal sign, meaning this is an exact answer, is 5 square root of 2. You can do math with that. If you found the square root of 50, which we know is going to be between 7 and 8, let me quit. Second, square root 50 is approximately 7.07. Bigger than the square root of 49, smaller than the square root of 64. Much closer to 49, though, so that's why it's just a little bit over 7. But we can't do the math with that. So unless you're asked for the approximation, you want to simplify to find the exact answer. Okay? So let's look at some examples. We'll start with numbers and then work with ones with variables that have leftover bits. Okay? So with 98, you see it's not a perfect square. You can check it to make sure. If you enter square root of 98, you're going to get a decimal answer. Okay? But that is one of your ones that you should recognize as not. Okay? All right. So you're going to have to find a factor pair of 98. Okay? List them in an organized, ordered manner. Or go to your calculator to help you with that list. If your list is in order, or if you're looking on the calculator, going down on the right, as soon as you hit the first big one, the first one, that's going to be your biggest. But remember, there might be others even over here on the left, not for 98, but there might be a 4 or a 9 over on the other side. Okay? That's all. There might be another perfect square factor, but you've got to choose the biggest, otherwise you're going to make a mess. So that will work. So first, I rewrite this as a factor pair with the perfect square factor. It doesn't matter if the 49 is bigger or small. That doesn't matter. What matters is the perfect square factor went first. By the product rule, I'm allowed to break this up into two houses. This can be rooted and released. And that is trapped. That's done. It cannot be released. It's the leftover bit and must stay under the radical. Okay, try 35. Does it have any perfect square factors? Uh-uh. 1 is always a perfect square, but 1 times 35 would get you nowhere. Yeah, 1's always a perfect square, but if there's no, can I do anything? 35 is not a perfect square, and it does not have a perfect square factor, so there's nothing, it cannot be broken down, either whole or in part. So that's it, that's the answer. It's not that it's non-real, there's no problem with it, it's just already as simple as it gets. Now, if you've got a different index other than square, you're still making the same factor list, either on paper or in the calculator. It's still, you're looking for factor pairs. But instead of looking for a perfect square factor, you are looking for a perfect cube factor. Now, the nice thing about cubes and higher ones is that the bigger your index or the bigger your exponent, the bigger the number gets faster and faster. So if you look at your perfect cube roots, 1, 8, 27, they start to get really big. And perfect fourth powers get even bigger, bigger faster. So 54 is not a very big number. You don't have to really worry too much about checking a whole bunch of stuff. The only thing that would work would be anything smaller than 54. And so it's only either going to be 27 or 8. If it has a perfect cube factor, then that means it's divisible either by 8 or 27. And if it's not, then you're out of luck. Or, it's no big deal. You just can't go further. Okay? So you can make your factor list, and the factor list is 1 times 54, 2 times 27, 3 times 18, 4, 5, 6 times 9, And then 8, no. 9, yeah, but I already got it. Okay? You see the same list on your calculator. Okay? So going down the right-hand side, oh, there's 27. There's also 9, okay? But you want the biggest one. Okay. Oh, no, there's not 9. See, that there, that's exactly the kind of mistake it's easy to make when you do cubes. You're not looking for perfect squares. Your brain gets trained to see perfect squares most easily. So, oh, perfect square. No, we're looking for perfect cubes. And the only thing perfect cubes we might have are going to be smaller than 54, so all we're looking for is 27 or 8. Okay? So the more you recognize that, you can just go, instead of doing all that, just think, is it divisible by 27 or by 8? Okay? If this were like 72, then you might check 64, 27, and 8. Anything smaller than the radicand. Okay? So you found a factor pair that includes a perfect cube. Put that first, 27 times 2. Break it up into 2 houses. Make sure they both have an index of 3. Root and release. And it's never a bad idea when you've got an index other than a square root, other than a 2, leave the dot in there if there's any, because if there's any question, especially when we deal with some variables that have exponents, smushing that up and mixing it up with the index gets really messy. It's not a big deal in my math lab where you've got boxes that are raised and all to type things in, but especially for your notes to be clear, and especially then for the exam, so I'm clear, it's never a bad idea to leave a dot if you've got an index other than 2. That really clarifies, it's still multiplication, but it clarifies, it separates, so I know what's the index and what's an exponent. You wouldn't want this to look like 3 cubed times square root of 2. Okay, good? Ready for variables? Okay, so as you can see in all of these examples, there's a leftover bit, except for this one which couldn't be simplified further. But so you've got something you can root and release, a perfect root on the left, and leftover bit that stays trapped inside the radical sign on the right. So when you're dealing with these problems, which look a lot like the problems we just did for 11.1 before we moved into the product rule, except when you look at these, square root, is this a perfect square? Is this a perfect square? No. Is this a perfect square? No. Is this a perfect square? What's the exponent? Odd number. So only even numbers are perfect squares. Multiples of 3 are perfect cubes. Multiples of 4 are perfect fourths. Okay? So not a perfect square, not a perfect square. Is this a perfect square? Yeah, because it's got an even exponent. Perfect cube? Perfect cube? Is that divisible by 3? Is that divisible by 3? So the number is not a perfect cube, but the variables both are. So if you look at what you have, and it's some combination of the number or the variables or both are not perfect whatevers, then you know you're going to be able to root and release part of it, hopefully, but part of it's going to be trapped. It's going to be left behind under the radical. So your first job with these problems is to separate the perfect roots from the non. Okay? So I'm going to rewrite this problem still under one radical bar. I'm going to write one long radical bar, and I'm going to put the perfect squares on the, this is index of 2. Okay? So I'm going to write the perfect squares on the left and the leftover bits on the right. 144, perfect square? Yes. So the whole thing, I don't have to break it into a factor pair like this. I just put the whole thing on the left. X to the 5th, is it a perfect square? No. But what I want to do is I want to take the most part of it. I'm going to factor it, just like I factored 98 into 49 times 2. And just like we factored x to the 12th into 10 and 2, we're going to break down this into x to the something times x to the something. Well, we can do x cubed and x squared, right? But what we want to do is we want to take out the most x's possible that will be a perfect square. 4, right. If it's a matter of a square, you're just taking one less. Okay?